Good morning, everybody. I'm very pleased that we have managed to clear the upper right corner of the screen because that is where all of the crucial information in this presentation will be located. So I'm very glad to be here at this 25th edition of the Sagan Workshop. Also happens to coincide with 25 years of transiting planets. Although, to be fair, it really has been 386 years since the first sighting of a transiting planet. That, of course, was Venus going in front of the sun. But it's only been 25 years that we've been able to do the same thing, but for stars that are so far away that they appear only as unresolved points of light. And we can tell a transit is happening by monitoring the apparent brightness of the star and seeing these short duration flux dips. A wealth of information can be obtained by observing these transits. Most famously, the radius of the planet. Let's see. Planet's radius from the amount of light that it blocks. When we combine it with the Doppler method, we can also learn the planet's mass, but there's a whole range of other properties. This is better? Okay. There's a whole range of other properties that we can learn about the planet's orbit, about the star that it's going around, and about the population properties of transiting planets, which will be our focus today. So first, though, let's just remind ourselves of the key transit observables. The first is the orbital period. That is the one number that we usually know best for any exoplanet, often to 7 or 8 significant digits. Then there is the depth of the transit, the fraction of the light blocked by the planet, which is roughly the square of the radius ratio between the planet and the star. And for Jupiter going in front of the sun, that's about 10 to the minus 2. For Earth, it's down by another 2 orders of magnitude. So a very challenging measurement. And the other main observable is the duration. The duration is a small fraction of the period. You multiply the period approximately by the radius of the star over half of the circumference of the orbit. So these are short duration events. For a hot Jupiter, it's typically a couple of hours. And for Earth, going in front of the sun, that's about 13 hours at most. The other key number that is very important and is in fact the main limitation of the transit method is the low geometric transit probability. So suppose there is a star and a planet going around in a circular orbit with radius A. Who gets to see transits of this planet? The answer is anybody that is viewing it from within this cone that has an opening angle of 2r over a, the angular diameter of the star as viewed from the planet. If you're in that cone and you look towards the star, you will see the planet projected in front of it. And as the planet goes around, that sweeps out a shadow band on the celestial sphere that is surrounding the star. And if you have to be within that shadow band to ever see transits of the planet. So the probability for a randomly located observer somewhere on this celestial sphere to see transits is the solid angle of that shadow band divided by the total solid angle of the sphere, 4 pi. That turns out to be the radius of the star divided by the radius of the orbit, which for Earth, for a planet at 1 AU going around a sun-like star, is only 1/215th. So the transit method has this tragic flaw. It is blind to the overwhelming majority of planets that might be out there. To appreciate the brutality of this selection effect, let's imagine that we have all of these stars, these gray dots, each represents a single identical sun-like star that has a single planet with a radius and a period given by the location in this log-log diagram. And let's imagine we observe all of these stars continuously for 4 years in a sort of idealized Kepler-like survey. Which of these planets would we detect? The answer is this. So a sample of transiting planets is very far from being representative of the planets that are actually out there. In the first place, we're missing a wedge in the lower part of this diagram because even if planets there do transit, they are too small for us to detect in the face of the noise due to the starlight's fluctuations or other effects. We do a little better for short orbital periods because within the time span of the observations, we collect more data during transits. We also see a tapering out in the detections for longer orbital periods, and that's because of the low transit probability, which gets worse and worse as you move farther away. And in fact, there's a point beyond which you have no hope of detecting a transiting planet simply because of the finite time span of your observations. You need to catch at least one transit, and preferably two or three, to be sure that you're looking at a transiting planet. So to calculate occurrence, by which I mean the average number of planets that exist with a certain radius and period around a random star, we not only need the number of detections from the survey, we need the denominator. We need to know how many stars did we really search for planets of that size and period, the effective stellar sample. And the number of effective stars that you have searched is not the number of stars that were observed by the telescope. It's lower than that. Each star contributes to that sum according to the product of the geometric transit probability, the radius of the star over the orbital distance, as well as the detection probability. That is, can we detect the signal in the presence of the noise, which depends on the brightness of the star, the radii of both bodies, the orbital period, as well as the detection algorithm. So a lot of work in transit occurrence studies is measuring that detection probability using, for example, inject and recover simulations, where you inject planets with known signals with known characteristics in the data, go through all the same steps that you do to do the actual planet detection, and see how many you can recover as a function of radius and period and other relevant variables. In fact, there's a wonderful and insightful paper that I would recommend to you from 2003, from the early days, by Pepper et al., that consider the case where a signal to noise limited transit survey. So you don't have a fixed star catalog. You just observe all of the stars that land within the field of view of your telescope. And they showed that the number of stars in your effective sample varies as the radius of the planet to the 6th power, and inversely as the 5/3 power of the orbital period. These are very strong dependencies. So for example, if you design your survey to have an effective search sample of 100 for Earth-like planets with periods of a year, then you will also be capable of detecting hundreds of more such planets with periods of only a few days, and millions more planets with sizes of giant planets. So these are extremely strong biases. So let's take stock of the pros and cons of performing demographics using transit surveys. We've already said that they're very inefficient because of the low transit probability. Most planets are simply missed. Furthermore, they are strongly biased in favor of large and short period planets. That makes the corrections that need to be applied, these detection probabilities, very tricky, and the results are very sensitive to the details of those calculations. And there's another problem I haven't mentioned yet, which is related to the possibility of multiple planets orbiting the same star. There is a strong degeneracy in interpreting the results of a transit survey between multiplicity, the number of planets that actually exist around that star, and the mutual inclination dispersion. How flat is the planetary system? How well aligned are those orbits? Let me explain that in a little more detail. So suppose we do a survey, and around a particular star, we detect only one transiting planet and do not detect any others. If mutual inclinations tend to be low, if planetary systems are known to be flat, then the non-detection of other transits suggests that those other planets do not exist, say in interior orbits with sizes comparable to that of the detected planet. On the other hand, if mutual inclinations are high, if the orbits have more random orientations, the non-detection of other transits has little bearing on the existence of other planets. Another way to think of it is that to interpret the results of a survey in terms of multiplicity, we need to make corrections for the geometric transit probability for multiple planets. And it's difficult because each planet going around the star creates its own shadow band. And we have to calculate the intersections between those shadow bands. The only people that get to observe two of the planets transiting are the ones that are within these intersections between the shadow bands. And these calculations are especially complicated if the orientations of the orbital planes are correlated with one another. So for example, if we want to calculate the joint probability that two planets are transiting, we can multiply the probability that planet one transits. That's very simple. But then we have to follow it up with the conditional probability that the second planet transits given the first one. And that's where the correlations between orbital planes makes this a difficult business. For this, I can recommend another paper by Brakensiak and Ragozin in 2016. They presented an algorithm and a computer code for actually calculating these multi-transit probabilities. And another fun thing that they did in this paper is imagine viewing the solar system from random directions. What would aliens see if they conducted a transit survey that included the sun? And the sobering answer is that none of them would ever see more than 3 planets out of the 8 planets transiting. And in fact, the most likely combination is only 2 planets, Mercury and Venus, transiting. And even that has a probability of only 6.8 times 10 to the minus 4. So you can see how difficult it is going to be to answer questions like, how common is the architecture of the solar system using a transit-based survey? So all of that sounds pretty bad, right? So why, nevertheless, do we consider transit surveys to be some of our most reliable and interesting information about planet demographics? So here's the happy news. First of all, we are very lucky that short period planets turned out to be abundant, because those are the ones that can be readily detected by transit as well as Doppler surveys. This is a sentiment that our first speaker, Didier Queloz, expressed, and I fully agree. We gained decades in our advancement of knowledge about exoplanets due to this lucky break. Second, transit searches are imaging-based surveys. We can use wide field cameras with many, many pixels, and so we can search hundreds of thousands of stars simultaneously for transit signals, unlike, for example, the Doppler method, where you need a high-resolution spectrograph and lots of light, and you typically observe one star at a time. So that helps to overcome the very low geometric transit probability. Third, surveys with space telescopes provide us with precise and homogeneous data sets, and that helps to correct for these selection biases. Remember, I said they're very fussy about the details, but at least we have some very high quality data sets to help us with that task. And lastly, people have gotten clever and found ways to break this degeneracy between multiplicity and mutual inclination. For example, by combining the results of transit surveys with Doppler surveys and with the incidence of transit timing variations, the perturbations in the measured transit times caused by the gravitational forces from other planets in the system. And I'll describe one of those techniques later. So now you are in a position for us to understand a brief history of transit surveys. So we will start in 2001, when there was exactly one known transiting planet, HD 209458b. It was discovered with the Doppler method. It was not discovered first by the transit method, but it was later found to transit by conducting photometric observations over the predicted times. Here you can see it on a sky map. I'm going to be showing you a series of these all sky equal area maps. And even though there was only one known at the time, it was very obvious that this was about to become a very big deal. Now that once we knew about the existence of hot Jupiters and how readily detectable they would be, many groups embarked on transit surveys using telescopes at various observatories around the world to try to find more of these. And by 2007, they had started to succeed and found 20 or so transiting planets. You can see here that they tended to concentrate on the northern sky. By the way, in these diagrams, the color of the point will tell you what kind of survey was responsible for the detection. And the size of the symbol, like on a star chart, tells you the brightness, the apparent magnitude of the host star, which is so crucial for determining how much we can learn about that planet. So these early surveyors were quite successful, but they did discover that it was more difficult than it might have seemed. And that's because although when you detect what looks like a transiting planet, a short-lived, low-amplitude dip in a light curve, you get all excited, you think it's a planet, it turned out to be at least as often an unresolved blend of an eclipsing binary star whose light curve would ordinarily feature these very deep, high fractional depth eclipses, but blended together with the much brighter light of a nearby star without any eclipses or transits, so that together the sum of the light resembles the light curve of a transiting planet. For definitive confirmation, the best way to deal with this is to obtain Doppler spectroscopy and confirm that the object orbiting the star has a planetary scale mass. And that is observationally very expensive. And so that really slowed the progress in this field for a while. So surveys that had used very small telescopes, say 10-centimeter telescopes, to observe stars over very wide fields of view, had a lot more success in doing this confirmation because the stars were so bright, compared with other surveys that had used kind of professional grade telescopes, meter class telescopes, to look at fainter stars in narrower fields of view. Just to bring that point home, let's look at some of those stars. So here is one of the brighter stars and a finding chart for one of those stars. Very obvious, bright star, very easy to get the light down the fiber of your Doppler spectrograph. And now let's look at one of the targets of one of those fainter star surveys. That's pretty messy. That's going to be a tough night at the telescope trying to figure out which star you're going to be observing. So the lesson, which was like a lot of things obvious in hindsight, is that brighter stars are better, a lot better. Another lesson is that space telescopes are better. So to illustrate that, here is a light curve of a transiting hot Jupiter made with a ground-based 1.2 meter telescope. You can clearly see the dip due to the transiting planet, but there are a lot of fluctuations in the measurements, and the measurement was interrupted just after the transit by the rising of the sun. Here is the same planet observed by a space telescope of similar size. That's a lot better, am I right? Not only do you get much higher photometric precision, but you can arrange for long, uninterrupted observations so that you don't miss these short-lived events. In fact, the data are so precise, you can see some interesting features. You see that little tooth that occurs in the second half of the transit? That happened when the planet passed in front of a dark star spot on the star's photosphere, causing a little reversal in the light curve at that moment. So clearly, space telescopes are better for this sort of work. On the other hand, space telescopes are very expensive, and there's a very long gestation period between coming up with the idea for a space telescope and actually getting it in flight and operating. And in fact, before this lesson, the brighter stars are better, had really been absorbed by the community. 2 different space missions looking for transiting planets had already been planned. The first one was a European mission called Corot. Its main target was actually stellar astrophysics, performing photometric measurements to study the vibration modes of stars, and did a wonderful job in that regard. As the mission was planned, it was also recognized it could do a transit survey for exoplanets, and so it added that capability to the spacecraft. They used a 30-centimeter space telescope in a low Earth orbit to monitor several relatively narrow star fields and look at the faint stars within them for several months at a time. And by 2009, Corot had discovered some planets. Those are the green dots here on this diagram.
That was great. But because of the camera's small field of view, they were monitoring relatively faint stars, and they had a really tough time confirming that those transit signals are due to planets. In fact, almost all of the signals they were able to confirm turned out to be hot Jupiters, the sort of planets that we were already discovering from the ground. So, in fact, from this point on, let us restrict our attention to the planets smaller than Neptune, the ones that were really quite difficult, bordering on impossible to detect from the ground. So let's do that. We'll wipe out all of the hot Jupiters here. And as of 2009, there were only two. There was Corot 7b, which was an important discovery made by Corot. It was the first transiting super-Earth discovery around a sun-like star. And then there was another object, GJ 1214b. This actually emerged from a ground-based survey called MIRF that used the clever trick of exclusively observing M-dwarfs. The smaller sizes of those stars allowed smaller planets to be detectable because the fractional transit depth is larger. So, as I mentioned, there were two space missions that had been designed before the success and the experience of those ground-based transit surveys had been absorbed. The second one, of course, was the Kepler mission. You already know, and we've already heard this morning from Eve, how revolutionary the Kepler mission was to our field by discovering thousands of transiting planets, including whole new categories of planets. It clarified the super-Earths and mini-Neptunes. It found the lava worlds, the super-puffs, the circumbinary planets, all sorts of wonderful objects. So this was a NASA mission that was first proposed in 1992 and was launched in 2009. Like I said, these missions have a pretty long gestation time. But in 2009 and 2010, Kepler started to deliver its first transiting planets. Those are the yellow dots. So let's now let the years elapse and watch those yellow dots accumulate. Thousands of transiting planets, but of course, they're all in that one little part of the sky. Kepler had a relatively large field of view for a telescope of meter class. It was 10 degrees on a side, but still far from covering the entire celestial sphere. So that left us in kind of a funny situation after the 4 years of the Kepler mission. We knew all about the weird and wonderful planets that exist in a particular cone within the Milky Way, the direction that Kepler was pointed. But the first thing that we always wanted to do after detecting one of those planets was to perform high-resolution spectroscopy, to measure the planet's mass, maybe even measure the planet's atmosphere. And we were usually stuck because those stars are simply too faint to be practical for such observations, even with our largest telescopes. Now, to be fair, that was not Kepler's mission. Kepler's mission was a demographic mission. They wanted to answer the question, how common are Earth-like planets? Whereas characterizing and following up on any individual planets was very much a secondary consideration. The more recent transit mission, the TESS mission, the one that is currently operating, was designed with the opposite attitude. It was designed after the lesson brighter is better had been absorbed, and its whole purpose was to find where are the nearest transiting planets? Where are the ones that we can suck out as much information as possible about the orbit, about the atmosphere, and so forth? And in particular, where are the nearest short period transiting planets, the ones that are easy to detect, easy to follow up on, and as we then knew, very abundant. So TESS was not designed to do a demographic survey. Nevertheless, as I'll describe, and as I think we'll hear later this week, TESS has contributed some important results to this subfield. So TESS is another NASA mission, actually had a significantly smaller budget than the Kepler mission and used much more modest telescopes. It has 4 10-centimeter telescopes as opposed to the meter-sized telescope of Kepler. But each of them has a much wider field of view, and it operates in a very wide optical bandpass. Just to give you a sense of scale, here is a life-size test camera, one of those 4 telescopes held by the principal investigator, George Ricker, with 2 of my fellow co-investigators that you may know standing beside him. I'm dwelling a little bit on TESS, partly because I'm involved with the mission. I happen to know the most about it, and also because I like explaining its orbit to an audience of planetary dynamicists, especially. The Corot spacecraft was in a low Earth orbit. The Kepler spacecraft had its own orbit around the sun, a heliocentric orbit. TESS's orbit is somewhere in between. It's a special orbit. It is in a high elliptical orbit around the Earth. That's the blue orbit there that we see. And that gives it long, uninterrupted periods, 2 weeks at a time, of continuous observing, while still being close enough to the Earth that we have a very high data rate and can send back much more data to the ground than Kepler was able to send with its antenna. Now, the usual nuisance of an orbit like this, the reason why it's usually ruled out, is because gravitational perturbations from the moon tend to destabilize such orbits. So the TESS orbit had to be very carefully designed. It is in a 2-to-1 mean motion resonance with the moon. And it's arranged, so this is the Earth-Moon frame of reference, rotating along with the moon's motion, so that at every apogee, the spacecraft is either 90 degrees, it's alternately 90 degrees behind or ahead of the moon, and that causes a partial cancellation of those lunar perturbations that allows the TESS orbit to be stable for many decades. So that's pretty neat. I think that was really the key to the success of our NASA proposal that was ultimately accepted. So that was fun, and TESS was approved by NASA in April 2013. And then 1 month later, the Kepler mission ended because one reaction wheel too many had failed aboard the spacecraft, preventing it from maintaining a steady pointing at that original field. So it looked like we were going to be in for a long period of inactivity in the transit world before TESS could get up there and operate. That didn't turn out to be the case. So the NASA scientists and engineers figured out that since the telescope was still just fine, it could be used to point reasonably stably at positions along the ecliptic plane for technical reasons. So it couldn't point the original field, but it could observe a series of star fields along the ecliptic plane. And so the mission was rechristened the K2 mission and operated between 2015 and 2018. And this was really important, not only scientifically. It observed a wider range of stars than the original Kepler mission had observed, but also sociologically, by keeping the transit community well fed and busy and training new students to get involved and to get ready for TESS and to continue this effort. So going back to our maps here, we left off in 2014. Over the next few years, as I said, the K2 mission turned on and started observing these star fields around the ecliptic, and that was great. And 2018 was when TESS was launched. Now, the way TESS works, the way it scans the sky, it aims to cover the whole sky, but it can't cover the whole sky at once. Each of those 4 cameras is pointing in a different direction, so that at any moment it keeps a tall rectangle on the sky under surveillance. And so we divide the sky into these so-called rectangular sectors, and TESS observes each one for a month before advancing to the next sector and the next sector and so forth. And then in the next year, it can do the same thing in the other hemisphere. So over the course of a little more than 2 years, TESS can cover most of the entire sky. Here is a mosaic of real TESS images covering the southern ecliptic hemisphere. So this was our first sweep around the southern hemisphere. And we've returned to it now twice to fill in the gaps that existed in the previous surveys of the southern sky. So we have a pretty complete view of both hemispheres of the sky now. The total sky coverage now exceeds 95%. And if you zoom in on any one of these images, you can see we're looking at a lot of stars. There are plenty of stars to search for transiting planets. One key difference between TESS and the earlier surveys, Kepler, for example, is that TESS is looking at more stars, it's looking at tens of millions of stars instead of 100,000. And it's looking at a very wide range of stars, young stars, old stars, hot stars, cool stars, whereas Kepler really focused primarily on sun-like stars. So that's what allows TESS to be useful for demographics. It is better at creating samples of rare transiting planets that Kepler might have missed because it didn't look at enough stars, or stars or planets around different kinds of stars that were not included in that survey. Also very important is that all of the data are publicly available with no proprietary period. And I think that's been helpful in getting as many eyes on the data as possible with all kinds of creative ideas. So back to our sky charts, we left off with K2 having sprayed the ecliptic with transiting planets. Then TESS came online, and in the years that followed, those light blue dots, the TESS planets, have come to occupy a large fraction of the celestial sphere. So today we have several hundred transiting planets smaller than Neptune, and they're around relatively bright stars. These blue dots are large, so it's much easier to measure their masses, use JWST to look at their atmospheres, and all the other things that we love to do. If we include the planet candidates, that is, the ones where we see a transit-like signal, but nobody has yet had the opportunity to confirm that it's a transiting planet, we can see even more of these. We now have on the order of 1,000 smaller than Neptune. And if I drop the requirement that the planet be smaller than Neptune, now you can really see that TESS is covering the entire celestial sphere. Except for that one annoying, relatively blank region. That's where it happens that scattered light from the Earth is affecting the TESS data. So we've tended to avoid that region, and we'll be filling it in subsequent phases of the mission. Okay. So that's a review of the history of transit surveys. Now let's do a brief review of the results, the demographics from transit surveys. Let's start with giant planets. Giant planets, although they're very well studied, they're easy to study, are actually kind of rare in short period orbits, the ones that show up in transit surveys. Only 5 to 10% of sun-like stars have a giant planet interior to a one-year period. Nevertheless, the Kepler survey was able to make a good contribution. In fact, Alexander Santarin and his group were able to make a useful contribution to the demographics of giant planets based on the results of the Kepler survey. So this is an example of a non-parametric occurrence function, where what they calculated is the number of detections divided by the effective search sample, giving the average number of planets per 100 stars per bin in period here. So there's no requirement for these bins to follow some smooth function. They're just plotting it bin by bin. And so you can see that the occurrence tends to rise with orbital period, with a possible peak near 3 or 4 days, and even a possible dip at a period of about a couple of weeks. So TESS has actually allowed for improvement in the demographics, at least of the shortest period of these, the hot Jupiters. So now we're looking at those results from the Kepler survey, but restricted to periods between 1 and 10 days. And the TESS survey, in an effort led by Sam Yee that we call the Grand Unified Hot Jupiter Survey, which actually includes contributions from many other groups as well, has given us better period resolution and clarified the location and existence of this peak at a few days, which might be related to the formation of hot Jupiters. For smaller planets, Kepler told us quite a bit about these. It allowed us to distinguish between sub-Neptunes and super-Earths, as Eve described, and also gave us the occurrence of these planets, which are quite common, with periods less than a year. So this is an example of the parametric occurrence function. This is from a study by Pedagura et al., 2018. Just happens to be the study I know the most about, but many authors have performed similar investigations, where you quantify occurrence, in this case, as the number of planets per star on average per unit log period. And by fitting a smooth function to this, you get these results like these curves that are drawn here, where occurrence of these small planets tends to be uniform in log period once you get to periods longer than about 10 days. And interior to 10 days, there's a sharp fall off in occurrence, possibly related to those star-planet interactions that we heard about from Eve or for other reasons. The radius distribution is even more interesting. We've heard about this already too, and we'll continue to hear about the radius function of small planets from the Kepler mission. One feature is that we see this very sharp fall off for planets that approach the size of Neptune and beyond. That is called the radius cliff. that has led to a lot of theorizing about why such planets tend to be rare, well, larger than Neptune. And then maybe even more famous is the radius gap or the radius valley. We love to use geographical terms to describe our histograms and parameter space that seems to separate the super Earth type planets from the sub Neptunes. So in the interest of time, I'm going to move ahead. Let's talk about the star. So another thing you can do from these transit surveys is get a better quantification of the metallicity effect. It has long been known that the occurrence of giant planets is strongly associated with the metallicity of the host star, which has been interpreted as a successful prediction or retrodiction of the core accretion theory for giant planet formation. Kepler has allowed us to do that for smaller planets as well. That's what's shown here. And so, for example, for periods between 10 and 100 days, the super Earths and sub Neptunes, the green and the blue here, do not show much of a change in occurrence with stellar metallicity across the range shown here. For the very shortest period planets, there does tend to be an upward trend. There is a positive association. The metal-rich stars do have more sub-Neptunes on average than low metallicity stars, but it's not nearly as strong as is observed for those giant planets, which may be another clue about the formation and evolution of those short period small planets. A more recent result from the test survey by Bowley et al. In 2024 extended this work to even lower metallicities than the earlier studies, and argued that the observed occurrence based on TESS observations of a wide range of metallicities leads to a lower occurrence at these low metallicities than you would have expected by extrapolating the results from higher metallicities. So naturally, they described this as a metallicity cliff, that there seems to be some critical metallicity below which occurrence falls off the cliff. So I am running short on time, but I think I can't resist talking about compact multiple planet systems. So this was a very important result of the Kepler mission, that lots of stars have multiple planets going around in tight orbits around the same star. And I mentioned before that it's tricky to break the degeneracy between multiplicity and mutual inclination. Well, these authors, Zhu et al., and this is from a review by Zhu and Dong, managed to do so by looking at the incidence of transit timing variations. Even if a planet is not transiting, so Kepler misses it, it can make itself known by pulling on the transiting planets. And so if you use both sorts of information, they were able to determine the actual number of Kepler planets that exist around stars, and they tend to be 2, 3, 4 planets per star with periods less than a year, and also argued, based on the data, that as you increase the number of planets, the systems become flatter and flatter. So the systems with 6 planets have very low mutual inclinations. Systems with 2 or 3 planets tend to have a higher scatter in their orbital orientations. Okay, moving along again. I will just end by showing you this slide, which you'll have in the slide deck for reference, to point out that there have been a lot of other studies that I simply haven't had the time to address, to look at occurrence versus age versus stellar mass, to look at the conditional occurrence of whether an outer giant, the presence of an outer giant, affects the probability of having a compact multi-planet system. There's the perennial question of how common are potentially rocky planets in the habitable zone. Kepler's original question still doesn't have a very satisfactory answer. And I'll point you towards a couple of review articles as well. So with that, I will end, and I welcome your questions.
Right, so thank you very much for this nice review. We have time for a few questions. We can start in the room. Anyone? Yes.
Hello, thank you so much for a great talk. I'm curious about if you are able to glean any information about the atmospheres of these objects, because I imagine in the light curve you might see some reflection from the atmosphere, like a giant planet, say.
Yes, definitely. In fact, the main purpose of the TESS mission was to find planets around stars bright enough to probe their atmospheres. They're not exactly demographic results, which is why I haven't concentrated on them, but there's a lot of activity getting phase curves of those planets to see the rise in brightness as the planet comes around and shows us its day side, as well as to use Webb and other telescopes to do transit spectroscopy. In fact, I think something like 3/4 of the transiting planets that are being observed by JWST, at least planets smaller than Neptune, have come from the TESS survey. So that was a very high-level goal.
Any other questions? Okay, yes. So one here and then online maybe. Okay. Yeah.
Hi, Josh.
Hi.
Alex from University of Notre Dame. My question is, with your demographic results, how concerned are you that at some point in time they are defined by detection biases and could change? And do you expect the Plato mission to help kind of assuage any of those concerns?
Good question. So yes, as I emphasized, transit survey, like if you didn't know any better, if you didn't know the history of this field, you would think it would be the worst way to do demographics. But we are saved by the factors that I described, these homogeneous, precise data sets. People are employing ever more sophisticated statistical methods to try to debias these results and do forward modeling. So I think the knowledge that I chose to present here, I think is robust. I think it will stand the test of time. Your second point, though, was about Plato. That's one of the things I didn't have time to describe. We will be hearing about it later this week from the PI. But Plato, as I see it, its main advantage will be kind of being intermediate between Kepler and TESS and giving us access to longer period transiting planets with periods of up to a year or more around stars that are reasonably bright, sort of intermediate in that respect. Sure.
Right. So now we take one online.
Yeah, this one has 3 thumbs up. You mentioned on test coverage, there's a small patch which is difficult to cover due to scattered sunlight and light contamination, I guess was the Earth's shine. So I was wondering in future phases how the mission is going to tackle it.
Yeah, I love that question because I have some slides that show it. So this is a sky map where the color shows you how many sectors, how many months of data have been obtained by TESS. This was the first 2 years of the mission. And then this is the next 3 years. And then this is more or less where we are now. And that one little blank part of the sky is that area that just cannot be advantageously observed because of scattered light. However, the orientation of the TESS orbit is changing. There is a Kozai-like effect that alters the orbital parameters of the spacecraft due to the combination of lunar and solar and Earth gravity. And that's causing that zone of avoidance to move on the sky. And so we've already started filling that in, and we have been at least provisionally approved to keep going for another 3 years to correct that deficit.
Yeah, so thank you very much. I'm sorry we are running out of time and we all want to have a bit of break. So let's thank the speaker again.